All right, in this video I'm going to go through a couple of examples of applications of L'Hopital's rule. I'm going to move from some more straightforward cases to some that are complex and some that are even profound. And yes, they really are kind of profound. I don't know, you'll see. All right, I'll try not to screw these up. So here's a pretty basic case. Limit as x goes to 0 of sine 2x over sine x. And you can see if we try direct substitution, just try that right down here, I get sine 0 over sine 0, which is just 0 over 0. Okay, so that's not going to work. So I will use L'Hopital, which means I'll take the derivative of the numerator. The derivative of sine 2x is 2 cosine 2x. The derivative of sine 3x, the denominator, is going to be 3 sine 3x. Now I check again because we saw an example last time where I kept using it. I used L'Hopital over and over again, but again, we have to check each time to see what happens when we try direct substitution. And in this case, when we try direct substitution, we get 2 times cosine 0 over 3 times, oh, I messed that up. That should have been cosine. You probably already saw that. 3 cosine 3x. So I get cosine 0, and that's going to be, cosine 0 is 1, so I end up with just 2/3. Great. So there's my limit. Used the L'Hopital, just needed to use it once. And this is an important one because this is, you can kind of see a pattern here. Anytime you've got sine something over sine 5x over sine 7x is going to, the limit's going to be 5/7, and so on. Things going to work the same way. All right, so that's a pretty straightforward case. Here's a case where we're going to have to apply L'Hopital twice. We actually saw this already once, but I'll show you again. So check again to make sure we can't use direct substitution. If I do that, I get negative infinity squared, and then this other stuff doesn't really matter, over e to the infinity. So I end up basically with infinity over infinity, which is an indeterminate form. If I go here, so I'll try using L'Hopital the first time, and I get 2x plus 4 over negative e to the negative x. Now if I try direct substitution here, right, I get 2 times negative infinity over negative e to the infinity. So I get negative infinity over negative infinity, and that's obviously that's the same problem as infinity over infinity. So that's also an indeterminate form. So I'll go back to this. That tells me that I can use L'Hopital on this second limit here, right? Because it's an indeterminate form, I can use L'Hopital. So I get 2, derivative of 2x plus 4 is 2. Derivative of negative e to the negative x is just e to the negative x again. Okay, now I can try some direct substitution. So this is going to give me 2 over e to the infinity, and that's just 2 over infinity, or 0. The denominator is going towards infinity, the numerator is staying constant, so we end up with 0. So what we had to do was use L'Hopital twice. But again, really important, each time we have to try direct substitution and see if that works. If it doesn't work, we can do L'Hopital again. All right, some cases it's going to be important to set up the limit correctly. Now you look at this limit as x goes to infinity of x times e to the negative x. Well, if I try that, I get infinity times 1 over infinity, which means I've got infinity over infinity. So that's an indeterminate form. The problem is I don't have f of x over g of x here, right? I've got something f of x times g of x. So I want to rewrite this limit so that it's in the form where I can use L'Hopital. So this is limit as x goes to infinity. Well, x times e to the negative x is the same as x over e to the x, right? So now I've got infinity over infinity, right? This is I didn't do anything here, I just rewrote it. So I still have that same indeterminate form. Now I'll apply L'Hopital. X goes to infinity, I've got 1 over e to the x. Now I can use direct substitution, and I'll get something, right? I get 1 over e to the infinity, which is going to be 0. 1 over infinity, or 0. Down here, the second one, limit as x goes to infinity of x times sine 1 over x. If I plug in infinity here, if I try direct substitution, I get infinity times 0. I don't know what that means, right? I don't know what infinity. It doesn't tell me anything about what's happening. Is it going to infinity? So there's two possibilities here, right? It's either infinity or 0. That's what it looks like. Two ways to read this, and I don't know which one it is, and I don't even know if it's either one. So what I'm going to do, I want to use lhopital, but I can't use lhopital until I've rewritten this in a way that's I've got one function divided by another function, f of x over g of x. So I'll rewrite this like this: sine 1 over x over 1 over x. Oh, I forgot to write the limit. I often do that. Limit as x goes to infinity of sine 1 over x over 1 over x, right? X is the same as 1 over x, right? So I can make this substitution. Not doing anything to it. I haven't applied lhopital yet. All I've done is rewrite the function. But now it's in the form f of x over g of x. We already know this leads to an indeterminate form. So I'll do my lhopital. The derivative of sine 1 over x, that's going to be cosine of 1 over x times the derivative of the inner function here, so the chain rule, right? Negative 1 over x squared over the derivative of 1 over x, which is negative 1 over x squared. I forgot to write the limit again. All right, now what happens? These guys cancel out, so I end up with the limit as x goes to infinity of cosine 1 over x. And that's not a problem, right? Because cosine, I can use direct substitution. I get 1 over infinity. That's cosine 0. And cosine 0 equals 1. So look where we started, right? We started with this infinity times 0. What is infinity times 0? I don't know. It doesn't mean anything, right? I mean, it's not that it doesn't mean anything, but it's not telling me anything about where this function actually goes. I do this. I get cosine 0. I do direct substitution. I end up with cosine 0, which is 1. Now I have an answer that the limit as x goes to infinity of x sine 1 over x is equal to 1. All right, here's the hard case. I don't know. It's a little harder because again, we don't have. It's an issue of setting up the limit correctly so that we have some function over some other function. Here we've got some function 1 over ln x minus some other function 1 over x minus 1. What we want to do is rewrite this. Well, first of all, we can see that this is not going to be any, right? What do we end up with? If we try direct substitution, we end up with 1 over 0, right? ln 1 is 0, minus 1 over 0. So we've got infinity minus infinity. And if you know what that is, you're smarter than I am. I don't know what that means. It doesn't tell me anything, again, about where this actually goes as x goes to 1. So what I'm going to do is combine these two fractions. I'll do, x minus 1 over x minus 1, ln x over ln x, and I end up with x minus 1 minus ln x over ln x times x minus 1. All right. Again, nothing's going to change here. Like our limit's still going to be the same. I haven't applied lhopital. All I've done is rewritten this function in here. Now, though, I have an f of x over a g of x. I've got a limit that results in an indeterminate form, and now I can apply lhopital. Interesting. Actually, I guess it is interesting to note that at this point, once I have it rewritten this way, it results in a different indeterminate form. It results in 0 over 0. You can check that on your own if you want. I'm going to go ahead and apply lhopital. Okay, so I've got in the denominator, I've got 1 minus 1 over x. And in the denominator, I've got, all right, this is a little tricky, 1 over x times x minus 1 plus 1 times ln x. Got to use the product rule there. Okay, now what happens? Well, if I try substitution here, direct substitution here, what happens? I get 1 minus 1 over 1 times 0 minus 0, so I get 0 over 0 again. So I'm no better off right now. Well, I actually am a little bit better off, as it turns out, but it doesn't look any better. But I've got another indeterminate form, which means I can apply L'Hopital a second time. So limit x goes to 1. I'll take the derivative of the numerator and get 1 over x squared. I'll take the derivative of the denominator, and you know what, I'm going to rewrite this because this is the same, this denominator is, I'm just going to, hold on, I'm going to erase this over here. This thing ends up being 1 minus 1 over x, so just make this easier. I'll distribute the 1 over x, so I get 1 minus 1 over x plus ln x. Now this is a lot easier. Okay, so derivative of 1 is 0, derivative of negative 1 over x is negative 1 over x squared, and I get derivative of ln x is 1 over x. All right. And I don't know about you, but I'm looking at this and thinking, oh, wait a second, this shouldn't be negative here. It should be positive because it was negative. This is negative 1 over x, so the derivative is positive 1 over x squared. Okay, you're looking at this and you're thinking, I'm no better off, right? Right? We're taking the limit as we go to 1. But what happens, actually? Look, do some direct substitution. You get 1 over 1 squared over 1 over 1 squared plus 1 over 1, which gives you 1 over 1 plus 1, which gives you 1 half. Whoa, that's kind of cool, right? You wouldn't have expected that when we started, that the limit as x goes to 1 of 1 over ln x minus 1 over x minus 1 would end up being 1 half. So we see this, what we had to do was first rewrite it so that it's in the form limit as x goes to c of f of x over g of x. And then we had to do L'Hopital once. Well, actually do L'Hopital once, which gave us this one here, and then we had to do L'Hopital again, which gave us this one, which it turns out that we could then use direct substitution. One last. This is a hard case, but it's I don't know. I think it's kind of, well, mind-blowing might be an extreme case. Well, I don't know. I think so. All right, this is weird, right? We've got limit as x goes to infinity of 1 plus 1 over x to the x. If I try direct substitution, what happens? Let's see. I get 1 plus 1 over infinity to the infinity power. So I get 1 plus 0, or 1 to the infinity power. Okay, if you know what that is, again, you know more than I do. You know, you might think, well, it's just going to be 1 because 1 times 1 no matter how many times, but it doesn't really work out that way. And what we're going to do is we're going to do this. Y equals 1 plus 1 over x to the x power. I'm just going to call this thing y. No, sorry. Scratch that. Sorry, I'm going to call this the limit as x goes to infinity of 1 plus 1 over x to the x power. So this is the thing I'm looking for. Right? I'm looking for the limit as x goes to infinity of 1 plus 1 over x to the x power. So I'm looking for the limit of y. So I'm looking for y. That's right. Now, I don't know exactly but I do know that ln y is going to be ln limit x goes to infinity 1 plus 1 over x, which I can actually just call ln y. I can just say that's the limit as x goes to infinity of ln, oops, sorry, I lost an x there, ln 1 plus 1 over x to the x. Now, I know from my rules about logarithms that ln y then is limit x goes to infinity of x times ln 1 plus 1 over x. Right? I can pull that exponent down and put it in the front of my my logarithm. Where do I want to go from there? Okay. And I've got, if I look here now, I've got, if I try direct substitution on this, right, I've got infinity times 1 ln1, 1 over infinity is 0, right, so I end up with ln1, which is 0, so I've got infinity times 0. I don't know what that means. That doesn't give me any information. So I'm going to use lhopital. Now to use lhopital, just like in the last problem, I have to rewrite this, put this in a form of f of x over g of x. So I end up with limit x goes to infinity of ln 1 plus 1 over x over 1 over x. And you can check it. If you try this, you end up, if you try direct substitution, you get 0 over 0 again. I'm not going to go through that. Just try it out yourself if you don't believe me. I'm going to try lhopital now. First time pass with lhopital, see what happens. Well, the derivative of ln 1 over 1 plus 1 over x, or the derivative of ln 1 plus 1 over x, is 1 over 1 plus 1 over x times the derivative of the inner function here, so which is negative 1 over x squared. And the derivative of the denominator, 1 over x, is just negative 1 over x squared. So again, just like in that other problem, these two cancel out, and I end up with the limit as x goes to infinity of 1 over 1 plus 1 over x. Now, what is this? Oh, now this is doable, right? Because I can use direct substitution here. I get 1 plus 1 over 1 plus 1 over infinity. This becomes 0, so I end up with 1 over 1, or just 1. So what was this thing again? This thing, remember when we started, that was lny. So we come to this conclusion that lny equals 1. Well, if lny equals 1, then y equals e, because ln e is the thing that natural log of which is 1. But remember what we started with, what we defined y as. Y was our limit. Y was our limit, the thing we were looking for to begin with, as x goes to infinity of 1 plus 1 over x to the x. So what does that tell us? And here's the profound, mildly mind-blowing part. It's that, I'll put it in a different color just to emphasize it. It's that the limit as x goes to infinity of 1 plus 1 over x to the x power equals e. And that's actually where e comes from, as far as I know. That would be like, yeah, there you go. So there's e. That's kind of cool. All right, I think that's all I've got for now. Yeah. So anyway, those are some hard problems, but you get the idea.